Hello, everyone. Welcome to episode 1 of No Exasol. In the previous episode, we discussed why analytics engines matter and why I started exploring Exasol. One thing you will hear repeatedly from customers, partners, and analysts is Exasol is fast. But that raises an interesting question. What actually makes Exasol fast? Is it faster hardware, more memory, better infrastructure, or is there something happening inside the engine itself? Today, we are going to look at the architectural foundation behind Exasol's performance. So, in this episode of What Makes Exasol Fast, we would like to see what all the components helps Exasol to perform faster, perform the queries faster, get the output faster. There are four architectural decisions: columnar storage, in-memory processing, massively parallel processing known as MPP, and an analytical execution engine with built-in automation. Each one is documented, each one is measurable. An XSL is built exclusively for analytical workloads, for its aggregations, column scans, large data sets. It's a big data sets. It is not for any transaction related queries or any, it's not OLTP, it is for OLAP. That distinction is why the storage architecture looks the way it does. Let's get deeper into it. See here, we need to spend some time here. To make Excel faster, there are four important pillars we need to deep dive and we need to understand the engineering behind it. The four pillars named explicitly in Exasol's official overview as well. Columnar storage reduces I/O by reading only query relevant columns. In-memory processing keeps data in RAM in the same compressed format used on disk. MPP, a massively parallel processing, distributes every query across all nodes simultaneously. And the execution engine self tunes auto statistics, auto indexes, and query caching. We will cover each one at a high level now, and then we'll go deeper in upcoming episodes. So, pillar one, columnar storage. So, what is columnar storage and how does it help? So, columnar storage and compression reduces the number of input and output operations and the amount of data needed for processing in memory, in main memory. Here is what that means in practice. In row based storage, every attribute of a record sits together on disk. Just take an example. If there is a sales data, if a query asking for a region and revenue, it still reads customer and product because they are stored in the same block. But in columnar storage, each column is independent. The same query reads only region and revenue. Customer and product are never touched. At scale, a 40 column table where your query needs only three columns. You're reading roughly 7% of the data a row based system would read. Everything else we talk about today builds on this. So, why does it matter? It reduces I/O for analytical queries, enables high effective data compression for per column that speeds up aggregations across millions of rows when you are querying a big data. The next one, pillar two, is in memory processing. The key detail that is mentioned in the official documents, I'll provide all the official links in the comment section so that you can go and you can check on yourself. Here, the data is compressed at column level with identical images stored in the main memory and on persistent media. The identical images, same compressed format in RAM and on disk. Most databases decompress data when loading it from disk to memory. XSL doesn't that way. The data is compressed on disk, stays compressed in RAM, and the query engine works directly on the compressed representation. There is no decompression overhead. Hot data set stays in memory. Subsequent queries skip disk I/O entirely. The official DB RAM sizing guidance starts at 10% of raw uncompressed data volume. That's how efficient the compression is. It matters for memory access, for magnitude faster than disk. Repeated queries on the same data stay in cache, reduces query latency when we do interactive analytics. We'll go deep dive of this, in episode 4. So moving on, massively parallel processing. This is one of my interesting topics, and when we go into episode 3, like, we will go really deep dive about massively parallel processing. What is the architecture behind it, how does it work and all, but I'll quickly touch upon at a high level what is this and how does it help Exasol to perform faster. Exasol was developed as a parallel system based on the shared nothing architecture. Queries are distributed across all nodes using optimized parallel algorithms that process data locally in each node's main memory. What is shared nothing? Shared nothing architecture means each node owns its own data, CPU, and RAM. When a query arrives, it's distributed to every node simultaneously. Every node runs it against its own local data in parallel. The results get merged. There is no master node. All nodes are equal. Adding more nodes linearly adds processing capacity, thousands of concurrent users without degradation. Again, as I said, now we'll go deep dive about this in our episode 3. And moving on to pillar 4, analytical execution engine. This is described as a self-tuning, but the documentation names 4 specific mechanisms, not a vague claim. um, Cost-based optimizer, statistics gathered automatically after every DML, no manual analysis. Auto index lifecycle, indexes created automatically for joins, dropped automatically after 5 weeks unused. Query cache. A select query and its results are stored. Identical queries served from cache, no re execution. Next one, auto table reorganization. When more than 25% of rows are marked deleted, the table rebuilds itself automatically. There is 4 documented mechanisms and not marketing. So how these 4 pillars are working together? So columnar plus in memory, columnar plus in memory, compressed column data read directly from RAM, no decompression step, no unnecessary IO. Columnar plus MPP, each node reads only its column segment in parallel. Throughout throughput, each node reads only its column segments in parallel. Throughput multiplies linearly with nodes. MPP plus execution engine, the cost based planner decides what to read and where to run it. All 4 together, every query finds the shortest path from storage to result automatically without manual tuning. So why this matters? Faster dashboards. BI tools gets result as faster as users explore, which would help for any decision makings as quickly as possible or in a real time. Faster reporting. The query cache means repeated queries do not re-execute. The scheduled reports and HADA queries finish faster because of this cache mechanism. Faster aggregations, sum, count, and across hundreds of millions of rows distributed across all nodes. Better user experience. When the data layer is fast, adaption follows. So what we will explore next. So that's what I have for episode 1. The intention of this episode 1 is to high level discuss about what makes XSL faster. As we just saw, there are 4 pillars, all documented and all well connected. In next episode, episode 2, we go deep into columnar storage, the actual comparison ratio from XSL sizing docs, and a feature called zone maps that skips entire column segments before reading them.